Good afternoon to everybody, and welcome to the Surgical Holdings Education Academy webinar on surgical instruments back to basics. We're going to be starting in a moment. I'm just waiting for a few more people to join on, so I'm just going to mute my mic for a sec and then we'll kick things off. Thank you. So for anyone just joining us, the session is being recorded, so we're going to share the recording after the session as well. Obviously, if anyone's hopefully everyone's okay with the session being recorded. Obviously, your web cameras are not showing anyway during this session. Okay, so we're going to lead into the presentation I'm going to go through now. Just got on the screen at the moment some key points for the day, and sorry, there's still some more people coming in. And so some key points for the day. So just a brief introduction. So I'm Dan Call. I'm the Managing Director of Surgical Holdings. I also chair the Association for British Health Tech Surgical Instruments Group. And so these webinars are something we've done in the past that we're relaunching under the Surgical Holdings Academy. There's going to be further webinars, and we have two more arranged or booked in for days that I'm going to share the information on these at the end of the session. So as normal with these Teams webinars, if you have any questions as we go along, if you could stick them in the chat, and then I'll attempt to look at these. I think midway through I've got a slide to pause and to take a look at a few questions if we have any come in. Equally, I'll pick some up at the end. This is a CPD certificated session, so anyone who's registered, whose email address that we have through the registration will be sent off to CPD, Continuing Professional Development, and will receive a certificate for attending this session. I think it's worth 1 CPD point for the hour. So if anyone is sharing computers, if you wish, and because it's only going to be done on basically whoever's registered, please send me in your email addresses and I can add these onto the registration. As I mentioned, the session's being recorded. So back to basics and surgical instruments. Where's this going to take us? So we're going to start off with looking at the origins of surgical instruments, the technicians that manufacture the instruments. Then we're going to look at the surgeon and the patient, and what the relationship there is in terms of the devices themselves. Then on to features and identifications of the instruments themselves, material selection, which is very, very important, and we'll come to that, and obviously vitally important part of the manufacture of the instruments. And then we're going to look at sustainability of repair as well, and also some maintenance tips along the way. So first, the origin of instrumentation. As part of the research I've done for these sessions along the way, I came across a great journal article here from the Royal Society of Medicine back in the 80s, the late 80s. And this was actually a paper on essentially the origins of the surgical instrument maker and how they came about, and the development of that, which I've always found quite fascinating. Here's a graphic that just shows how through the over the years the surgical instrument maker, or technician as we know nowadays, has evolved interestingly, all the way back to the flint toolmaker. So what we would known as the Stone Age and then the Bronze Age. Interestingly, there are other elements to this as well. As you can see, blacksmith, armorer, all these different factors coming in that, or different professions that are related in some way to surgical instrument making or an element of the surgical instrument making. So below, you have what is deemed, and this is bearing in mind back in the late 80s, as the surgical instrument maker as it is now, as they are now, sorry. So having taken on various different elements of these skills and obviously being able to manufacture a range of different instruments. What's interesting about this, though, and when I came into the profession myself at 16, the instrument makers were very much focused on making a particular area. So, for instance, we have here a brass worker. So we would have a soft metal specialist, and then we'd have a specialist potentially in forceps or scissors. So as the role itself has developed, we're now left with obviously a lot more instrumentation that's not manufactured in the UK, and therefore an instrument technician that has built in a probably a wider variety of skills across multifaceted range of instruments, and a lot of that is to do with the repair and maintenance on the instruments nowadays, and seeing lots of different types of instruments. So anyway, as I mentioned, we're going all the way back to the Stone Age, and so yes, the surgical instrument maker did indeed come directly from the caveman, and I have photographic proof of this in the next slide. And this is me looking literally like I've crawled out of a cave at the age of 16, trying to find my way in the field of surgical instrumentation and learning alongside my colleagues at Surgical Holdings. Another comment here from the Journal of Royal Society of Medicine, as I mentioned, the British instrument makers have not, on the whole, been very innovative in the design of their products, which seems a bit harsh. However, when we look at a lot of the instruments that we're using nowadays and reflect back to the original designs, I can see why they've come up with this. So look at the Spencer Wells here. If we look back to the late 1800s, when the Spencer Wells was invented or created, and by the original surgeon who came up with this, Mr. Spencer Wells, you can see now that the designs themselves haven't evolved too much. So there isn't a new forceps which has taken this place of the Spencer Wells. The Spencer Wells is still used. However, you can see the introduction of the box joint on the right, which we commonly see in a lot of instruments, artery forceps, needle holders, versus a screw joint, which was the original forceps design. I think, interestingly, and I'm going to show you some images later, I think perhaps the screw joint nowadays might be a better design, perhaps because it can be taken apart and cleaned, whereas the box joint has its own challenges. But obviously, just to show you that there isn't a great deal of evolution. Just some slides just showing instruments across the ages. Obviously, there's been evidence of instruments through Egyptian times, Roman times, and how instruments have been designed from different materials, and then coming through to the modern day. Obviously, over 100 years ago, the introduction of stainless steel, which is widely used in surgical instruments. Of course, now we have laparoscopic surgery, which is widely used, and indeed also robotic surgery now. However, a lot of these instruments are, again, more or less the same devices as the instruments that have been used for, say, in some cases 100 years, just on longer, obviously just of a longer length because of the nature of how they're used in laparoscopic surgery or robotic surgery. So the nomenclature of an instrument. So what's in the name, and how does the name become such for the instrument itself? And this really is just a breakdown of how those instruments are named. So if you think of, for instance, a Spencer Wells artery forceps, Spencer Wells being the surgeon that designed the forceps, artery being the area of the anatomy that the device is used on, and forceps being the type of device, and that's obviously through all different types of surgical instruments, you can see that pattern. So obviously you might have Mayo dissecting scissor, or you could have Mayo Hagar needle holder. So the breakdown generally works the same, and I'm just going to take you through another example of where this has come from and how it relates to the anatomy as well. So an instrument design starts with a medical issue. So here you can see this this poor chap here who's got an issue with his hip, which may be quite a mild issue at the moment, but eventually it might look something like this. He might have a major problem with his hip, and he might have a breakage. So this is generally how the idea behind, I guess, any surgical device is needed, a problem that the surgeon is looking to fix for that patient. So in this case, osteo, meaning bone, otomy, meaning to cut into, and ostomy means to create an opening. So to go back to reflection on the nomenclature of instruments, in this an example I have here, a capener osteotome. So obviously we're combining the words osteo and tome, using those previous terms, and that's how the instrument's getting the name. So in terms of capener, again, reflecting back to my journal article that I've mentioned a couple of times now, and I can't actually see that. So in general, the typical surgical instrument maker seems to be very conservative, and to have been deferred entirely to the whims of his customer, the surgeon. So in this case, very famous surgeon, Mr. Norman Capener, who very famous orthopedic surgeon, and that's where the capener osteotome is named from. Obviously operated very famously from Royal Devon and Exeter. One thing I was going to mention earlier when I was discussing around the origins of surgical instruments is actually, again, something that's fascinating me, is how I was looking at where a lot of the instrument companies were based in the early 1900s, and actually now probably the most expensive retail street in the whole of the UK, Bond Street. And they would actually have the instrument companies would actually have their showrooms in Bond Street, and the surgeons would come to Bond Street and look at the instruments that obviously they wanted to buy. So very different days now. I don't think Surgical Holdings, unfortunately, could afford a premises on Bond Street or New Bond Street, but you never know. So we've learned a bit about where the origins of the instruments come from, and now we're going to look at material selection. And I'm just going to make sure there's no questions. Let's have a look in the chat quickly. Okay, good stuff. Great to hear lots of people are joining us. As I mentioned, if you have any questions along the way, please pop them in the chat. Right. So material selection. This is very, very important, and I guess it's the biggest positive and negative around stainless steel and stainless steel that's used for surgical instruments. So this is actually a piece of iron ore, and iron ore makes up the majority of the composition of the stainless steel that we use for our surgical instruments. For around 70 to 80% of those instruments is iron, and this is iron ore, similar to iron oxide. So in the surgical instruments themselves, you would also have other elements, so carbon, nickel, and chromium are common elements that will make up that alloy for the stainless steel. So this is iron oxide. This is iron in its most stable state, and we've got to remember is the association with iron, and obviously the color, which is orange, very, very similar to rust or corrosion, and again remembering that this is iron in its most stable state. And even if it's in a nice alloy like stainless steel, it will do whatever it can to get back to that most stable state. So that's why obviously we use different chemical elements in the makeup of the stainless steel to create a stable environment for our surgical instrument steel. Of course, when we're taking our elements, they're smelted down, and the stainless steel is obviously created. And if we look at the world a map of world iron ore mining, this is a few years old now, but it's still quite key to our understanding of why nowadays a lot of surgical instruments are made in Asia. And you can see here obviously a very high density of iron ore mining in these areas. So as we can see, the largest steel producing countries, China, India, Japan, the States is also on that list, as is Germany. But of course, being the biggest availability of those of those materials that we're using to make the surgical instruments, of course, a lot of the instruments nowadays are made in Pakistan. And that's not for me, having instruments made in Pakistan. Obviously, we're going really where the resources are and where the steel is available. The crucial part is to have the correct steel and to be following the correct standards. And here's just some a few standards that apply to surgical instruments. So we have here. Well, I've listed the Medical Device Directive here. This, of course, we've got the MDR now, which is overtaken that as we transition towards the MDR. ISO 7153, and that is probably the most important standard with regards to surgical instruments. And obviously this is guidance for what instruments should be manufactured from when we're making instruments, and gives the precise breakdown of the different types of composition. So whether the steel is from Germany or from Pakistan or from the USA, it's crucial that it's meeting these requirements. And the reason for this is, of course, it depends on the application. So obviously different steels have different applications. Very, very important. I think a lot of Japanese steel is used in surgical instruments nowadays. And again, providing that meets the right specification, then it should be fine to use for surgical instrumentation. I'm going to tell you a few reasons why that is along the way. There are also some British standards. So we have the, again, very old British standards, BS 5194 series. There's specifications for things like scissors, giving advice on what materials your scissors should cut. Also dissecting forceps and other articulated instruments. So there's checks, things that we do in-house, for instance. So making sure that the forceps clamp correctly, and these are tested through these standards and different tests and recommended tests in these standards. Obviously, we have other elements or other standards that are utilised when we're manufacturing instruments, or generally as manufacturers of instruments. So ISO 13485 is obviously a very, very, very common standard for medical device manufacture. I also have neglected to mention UKCA marking, and obviously this is something that applies to the UK for well, I guess for a number of different products, but we're currently again seeing what that regulatory landscape is going to look like. And if anybody wants to put anything on the chat about that, then please feel free to do so, because that would be a good thing to discuss. So stainless steel itself, the stainless steel that's used for the manufacture of surgical instruments is martensitic. So that's a magnetic stainless steel. And this was actually discovered by a guy called Harry Brearley from the Brownfirth Research Laboratory in Sheffield, England. And actually he was looking at the time for a suitable stainless steel that could be used for gun barrels, and discovered this martensitic stainless steel, which is perfect for the manufacture of surgical instruments. And just to give you a bit more insight why, you have various, obviously, as I've mentioned, chemical elements that go into these different stainless steels. The common martensitic stainless steels that are used here for surgical instruments, we have the A, B, C, and D. You can see here the C, which represents carbon. Different levels of carbon for different types of steel, for different suitabilities for surgical instruments, and increasing levels of chromium as well. So martensitic steel is considered to be a reasonably corrosion resistant stainless steel because of the presence of the chromium and other elements such as manganese, nickel, very small element of that as well. So just to give an example, and I'm going to reflect back to Mr. Capener's osteotome that he very kindly designed for us. And he would obviously, when he was wanting to use this instrument on the hip, repairing the hip that we saw way back at the start of the presentation, he'd want that to be obviously very, very sharp and robust. But of course, although it might be sharp. You also need that sharp edge to be retained. So obviously you need it to be hard and a resilient edge. And to do that, you need the correct steel. So for this particular device, you need a specific level of carbon, and that comes from ISO 7153, as we can see at the top of the page. So between 0.42 and 0.5, that carbon then enables you to achieve a level of Rockwell hardness, which Rockwell is a measure of hardness. And unless you get that hardness, if it's too soft, when you use your Capener osteotome or chisel, then that won't retain that hardness. It will become blunt very, very quickly. It won't be fit for purpose. And Mr. Capener patients will probably not be very happy with the outcome of their surgery. So that's very, very important and crucial to ensure we're hitting these correct parameters. Chromium, of course, very, very important, because this allows us to achieve the passive layer on stainless steel, which I'm going to give some information on too on the next slide. So passivation actually is a natural occurrence, and this is simply a reaction between oxygen and chromium. So obviously you've got the chromium in the steel, oxygen naturally, the two react, and you get chromium oxide, which is a protective layer as little as 30 nanomicrons thick, so very, very thin. And that can be the issue with that is it can be very easily damaged, very susceptible to damage. That can be through mineral damage, blood, scratches, laser marking. Can also affect it if laser marking isn't passivated or treated appropriately. So very, very important to understand that. And don't forget, just sitting under this layer, of course, we have our iron as well, which is dying to get back to its most stable state. So to have an understanding of how this all works, it's a fairly delicate situation here. And as manufacturers, we can also achieve this passivation process by using different acid treatments. Again, these are referenced in the British standards to be followed. And using acid, you can oxidize the steel, and it just speeds up that natural process, which is very important. Obviously, that when we're supplying instruments into hospitals, that you followed a validated process that you can prove actually will do what you say it does, and provide your customers with an instrument that is corrosion resistant and fit for purpose. So yeah, just to finalize on the material element, I mentioned stainless steel, and it is stainless steel. Here we have an example on the screen, something I'm sure you've all seen on at some stage. Maybe it's an old rusty old garden gate like I've got. Iron plus oxygen plus water equals hydrated iron oxide, which is rust. And of course, we want to avoid this with surgical instruments if at all possible. I've mentioned the importance of the steels, the correct chemical compositions, and the correct elements that obviously go into that stainless steel for instruments. But we see examples all the time, and a lot of this is through repair and perhaps a lack of skill and a lack of technical understanding about what's important when making instruments. So examples of incorrect repair materials used that aren't to ISO 7153. So these are a couple of things we've seen recently. Funnily enough, on osteotome again, bit of a theme, but this came into us to look at for repair, and it was broken. Upon investigation, we could see a brass pin had been used, and to actually hold, which would go through the hole. I don't know if you see the hole there, to pin the osteotome into the handle. Obviously, there's no problem with pinning this into the handle, but you've got to use the correct materials. And brass is too soft. It's not in ISO 7153, and it's not suitable. Mild steel we see used regularly, and I think this is again because the lack of availability of good quality surgical grade stainless steel materials. So someone's done a lovely job repairing this orthopedic reamer. They've put a new end on it. Looks like it's been nicely turned up. However, completely pointless, as the wrong material has been used, and it's gone very, very rusty very, very quickly. So mild steel is not suitable to be used at all. We see this a lot on screws and rivets. Mild steel is used instead of the correct stainless steels, and it's just not up to the required standards to do what it needs to do. Another challenge that we have to consider when we're looking at the materials we're using for surgical instruments is water. And Here's a map of Wales and England, just showing the variation of source of potable water throughout, as I mentioned, England and Wales. And you can see the variety there. What that means is, though, we get a big variety of the different minerals that that are in that water. And although, of course, we do treat water and we use treated steam, RO steam, there are still obviously issues to overcome. You can just see, and I just wanted to give the example of the difference in the chloride levels. For instance, in Cambridge, we have a level of 100 versus a level of 20 in Manchester and London, and alkalinity the same. 260, 250, 15. So big variety, and a big difference of how these minerals or levels of minerals would affect stainless steel in the surgical instruments. As I mentioned, of course, we've got to think about the iron, the damage to the passive layer, and things like chlorides and high alkalinity will damage those passive layers, particularly if you've got a scratch there present on the instrument, or a slight imperfection. That will just speed that up when we're considering things like pitting on surgical instruments. If in the presence of particular minerals such as chlorides, you don't want to end up with an anodic reaction, which can cause pitting on a device. So where is water used, and where and when? So obviously taps, immersions, washer disinfectors, steam generators, condensers. Obviously, as I mentioned, these are treated. Chlorides can be very detrimental. This is what damage of chlorides looks like on the surface of steel. So you can see these little marks here, which look like sort of pit startings of pit potential for pit marks. And as I mentioned, pitting is something we definitely want to avoid. Pitting can be, you'll see a slight little mark on the surface, but under the surface there could be a much bigger corroded area. And as I've mentioned, that is because of the nature of how pitting works, and it's an auto-catalytic process, and in the presence of certain anions such as chloride, that's accelerated. Chlorides can also be found in blood as well, of course, as well as naturally in water. So quality, there's a great deal more to it than just a nice shiny looking surgical instrument. There's a lot more going on on the surface and underneath the surface of the steel that we've really got to appreciate when we're trying to take care of our instruments and ensure that they are fit for purpose for the patient. Of course, we can do some due diligence. We can do some material testing, and that will allow us to see what the steels are have they got the correct breakdown of chromium and iron, and that is something that as a manufacturer that we carry out to ensure that our customers and ultimately the patients are getting the right materials used on them when the devices are used. Surface finish is also something that I think is overlooked quite a lot, and research from the Stainless Steel Association here. I'm just showing a couple of images that I've taken from an article from Honus and Harrison, basically showing that the smoother the surface finish, the better the corrosion resistance is for the stainless steel. Something that is fairly common sense when you think about it. A rougher surface, there's therefore more surface area, therefore it's harder to dry if you've got an instrument that's been washed through a washer disinfector. The smoother the surface will decrease the wettability of the steel, and that is if water lands on a surface and dissipates, you want it to dissipate as quick as possible and to run off effectively rather than sit on it, because if it sits on it, you've got a chance that it could damage the steel. So the smoother the surface, the better. And that can only really be achieved, well, either manually or through automated processes, but really working those grains of the stainless steel. And you can see here, to taking back the surface to under 0.2 microns is something that we would do during refurbishment. But you can then, of course, potentially do a sandblast over the top if you want to change the presentation of the steel. But this is something that's really important when considering how important refurbishments are as well, because we've got rougher surfaces on devices where they've been used, and you can refurbish these devices. So this is an example of a duo finish, and towards the back of the instrument you've got an anti-glare, which is a sandblast that's applied over the top of a really bright, highly a very fine, bright polish finish around the distal working end of the device. Obviously, this ensures that things that like blood and it's just improving the cleaning efficacy of the device. You would finish the entire instrument in this bright polish finish first of all, and then you'd sandblast the back to achieve that. So let's see if we've got any questions that have come up so far along the way, as I try to work Teams and check it out. Okay, right. There are no questions as yet, which is fine. And we'll pick up at the end and see where we go. Okay, so onto instrument features and identification. And this is a bit more practical guidance on the actual instruments themselves rather than talking about what's inside them. So first of all, I just wanted to show a pretty obvious one, but something we see quite a lot is single use or reusable. So the devices that you've got on your trays nowadays, we often see a combination of single use for things like suctions and specific devices that perhaps that need to be single use. And of course, we see a lot reusable, but you should not. I've just seen I've got 1, 2 with a strike one way and one the other way. So I'm sure one of those is incorrect. Somebody will quite happily tell me that. But yeah, so of course, what we don't want to be seeing is that a device has been reprocessed and it has this do not reuse number 2 on it, because that is very, very important. That perhaps that device isn't suitable to be reused. The steels might not be to ISO 7153, but they might be perfectly suitable for being used once. And obviously, as I mentioned, a lot of the ISO 7153 importance is about the reprocessing the device to ensure it can be reprocessed. It's got the amount of chromium, so you can have a steel that's suitable for single use but not suitable for reuse. So that's very important to bear in mind. So common instrument features and where they might be found. I mentioned box joints earlier, and the example I showed was Spencer Wells, and we're mentioning Spencer Wells, obviously mosquito forceps, artery forceps, also needle holders. You'll see box joints. So this is a very common feature. Screw joint, I think, of course, very commonly on scissors, and that probably is, I guess probably 95% of the area you'll find screws used on. Ratchets, so this is a ratchet here. So we've got some examples of some self-retaining retractors, Norfolk and Norwich, Travers, Western Wheatland retractors, and they have what we call a ratchet. So other people might call it a rack. Sometimes these have like a hollow cut out of them, which is the more modern version. Funnily enough, there's a screw there again, so we can see obviously that does crop up in other areas. So teeth, when we talk about teeth on surgical instruments, you can see here we've got examples of Littlewood's tissue, Alice tissue, Lane's tissue. Some have 1 into 2 teeth, so that's like a meshing of the teeth. Others might have 2 into 3, 3 into 4, some even more. So that they're called teeth, and that's where you'll find them on the end of the instrument, often for gripping tissue. I've got a rack here, so again, some people might call that something slightly different, but again, found on artery forceps, needle holders, and that's something that allows you to adjust and set the instrument at a certain level of tension. You can do quite a nice little drop test with a rack, so to ensure your instruments are set correctly and aren't going to spring off the rack during use. If you drop them onto maybe a softer surface from about 30 centimeters, if they spring off the rack, then they need to be reset. Probably should go to your repair company to look at. Scissor blades, pretty obvious that they're scissors and they're used for cutting, and you have blades on scissors. Lumen is a term that we hear quite a lot when we're talking about trouble of cleaning stuff. So as I mentioned, suctions quite often single use, and for that reason that they can be quite tricky to clean. So yeah, so we've got examples: American Adson, McGill, Zollner, all common suctions. Serrations. So you'll get serrations on artery forceps and also on clamps. the difference here, you can see at the bottom of the page, you've got serrations and atraumatic teeth here. So both are serrations, but the serrations on the left, which you'll see on artery forceps, are slightly more robust, slightly more aggressive. When you're using them on more delicate areas, that surface area is reduced to what we call an atraumatic teeth. So it's a slightly finer serration, but also some of this serration is taken away, and you'll see there's a sort of a line either side of it, and that's to reduce the surface area that's clamping on those delicate areas. And we mentioned there DeBakey clamps, Dera, Coley, all these clamps that are used in cardiovascular thoracic surgery. Tungsten carbide tips, again, very common. Needle holders, you'll see most of them will have TC, and that's what TC needle holders look like, and the term bow, of course, on a scissor. Bit more detail there on the left again, and I'm happy to share these slides or any information in them, so you can see here that atraumatic jaw and traditional serrated jaw described again. Over on the right, I just wanted to show the sort of the difference in some of the designs of the forceps and the clamps. Here we've got a Satinsky. You'll see multiple angles, and obviously this poses a bit of a cleaning challenge as well, because of course you've got different grooves and angles to get into on these jaws to clean them. There's also the factor to bear in mind that there might also potentially be burrs, which you have to look out for, that could occur if the device is damaged, or even sometimes when they're manufactured. These should be they're checked under microscopic conditions to ensure that these burrs are removed. But obviously, just to show you the difference between the two, a basic serration and atraumatic. And then we have differences of types of forcep. So here you'll see the jaws, the teeth that I mentioned there, versus a serrated, like fenestration jaw. So you're two different tissue forceps, two different types of jaw, and this makes it even more challenging when you're trying to learn about your instruments if you're new into the industry potentially, or just refreshing. But it's just good to be aware of the differences, and that there isn't one size fits all, because these will be used for different areas in the anatomy or different areas of the operation. And atraumatic teeth also appear on forceps, so dissecting forceps. We've got some DeBakey dissecting forceps here. One thing that can get quite confusing is when you see the same instrument but with teeth and serrations. In this case, quite often you'll get a Makindo and a Gillies, but you can see here that the Makindo has these longitudinal serrations and traditionally is serrated, whereas the Gillies has horizontal serrations and traditionally is toothed. And quite useful things to look out for if you're looking at your trays and you see this longitudinal serration, then you know that it's a Makindo. Unfortunately and confusingly, some companies have actually created a 1 to 2 teeth Makindo as well, but generally, as a rule of thumb, that isn't the case. So different types of retractors, handheld retractors such as Langenbecks, Cocker Langenbecks, have this type of handle. Some might have a slightly different handle, but essentially the same thing. Then we have different retractors, what we regard as self-retaining retractors. So the Norfolk and Norwich, Travers, Wheatlanders, Wests, all have these ratchets, essentially, so you can clamp so you can use the retractor and leave it in situ, and it's held under the tension, and obviously with the aid of the rack. And then you've got the bigger abdominal retractor type, this type of retractor here, which has got a bar, and the blade slides along the bar and can be positioned and held tightly. So they're the different types of retractor, and a very different type of retractor that you'll see. So this is a Bookwater on the screen, but there are other versions of this sort of thing as well. And this is actually clamped onto the table post. So you'll see the retractor blades are on little ratchet mechanisms here. You've got a ring that is then attached to a table post, and this allows the surgery to be prepared, or the surgeon to prepare the blades at the different angles they wish, different types of blades, loads of different combinations, different angles. But again, just to show you the different types. I mentioned needle holder jaws earlier, and we have the tungsten carbide needle holder jaw here, and obviously it's a very hard jaw that's vacuum brazed into the device. Two different types here. Again, we've got different coarseness of insert. So a Crowwood is a finer needle holder, which might be used in plastics. Mayo Hagar is your standard needle holder on lots and lots of different sets. And this is what this gold bow generally means. So 2 gold bows denotes tungsten carbide. Mayo Hagar in this case. 2 gold bows, you'd think also a tungsten carbide insert. However, this is almost like a sort of welded padding to this scissor. So it's slightly different, but much more robust, again, for the reasons of the needle holder. And tungsten is harder than ultimately the needle material that's used, and that's why, because if we used the surgical needles without the insert, they would just they would damage the tips of the needle holders because they would be too soft. These are the different types we've got. So we're going from a micro all the way through to coarse, as I mentioned, for heavier gauges, and that's really based. The finer you look at will be for a fine needle for finer areas of surgery. 2 black bows is supercut, and that in this case is a strabismus scissor. Some different examples of supercut scissors here, and that's what supercut looks like. So it's one micro serrated edge which provides your grip, and the other edge which is a really ultra sharp edge that you might get in a barber's sort of razor, that sort of sharpness. So combine the two and we get supercut with tungsten carbide, which provides us with a very robust scissor. So as a quick guide here, we have one we didn't mention at the bottom that we see sometimes, one black bow to denote a left-handed instrument, a left-handed scissor in this case. You might also see some different coatings. You'll hear ceramics mentioned. A lot of these, the gold coating, in this case, will probably just be just like a gold plating, but there are some other PVD associated coatings, sort of thing you might see on Kerrison rongers. So they're tungsten, tungsten aluminium nitride and titanium nitride. Sorry, titanium aluminium nitride and titanium nitride. They give basically for the Kerrisons reduce friction and increase the cutting ability, make them tougher basically and more hard wearing. In this case, we'd coated some instruments here that this was just to distinguish them from some other instruments, but generally when you see a coating there is a need for it, or there is a reason for it. So just going on to maintenance and refurbishment now. I'm going to run through a few important points on this. So why maintain instruments? Well, this is exactly why. This is a picture of a Kerrison ronger that we took apart and that came in for repair and had lots of yucky carbonized bioburden inside it. So obviously, if we're not performing these checks and these maintenance, we don't get to see this sort of thing and deal with it. Obviously, an important reason nowadays, sustainability, when we try to move from a linear economy of taking from the ground, manufacturing, disposing, to circular economy, manufacturing, use and repair and recycle. So surgical instrument repair and device repair can form an important part of this. We've done our own work on this, and actually some recent research demonstrates a 95% CO2 saving versus new manufacture. So for the repairing device versus manufacturing new, it's a massive carbon saving. Surgical Holdings have made significant carbon savings in the 12,000 instruments we repaired back in 2023, and a big net saving around this. So this is something that's becoming more and more prevalent. And just some examples of some different processes used in repair. So for instance, we've got coating, so tungsten for potential. In this case, you've got Murphy skids. So obviously there's some electrosurgical coating. Here's how we do our needle holder brazing, induction brazing, obviously grinding, laser welding, passivation. bench fitting, drilling, welding, and lots of other different processes go into it. So as I mentioned at the start, there's a big difference now in how the modern day surgical instrument maker and the different techniques they use, the different skills they have, and of course, I suppose the improved technology they also have to their hand. Things like laser welding is utilised and is very important for sealing up gaps in instruments where water and bacteria could sit. So just going to go through some guidance around some checks on instruments now. What can we do? What can we check when we're trying to take care of our devices? So obviously scissors. And I'm just going to pick out some of these key ones. Scissors, checking for damage or cracks around the screw areas. They often get overstrained and that can be an issue, particularly if the lubrication's not used. Obviously using test materials if you can to test the scissors are important. Clamps, the biggest one I mentioned on this is burrs, checking for burrs in the clamps, making sure there's no burrs, and obviously you can look at this under magnification. And what I mean by burr is a small break off of a part of the device around the teeth. Making sure that the ratchets clamping correctly is also very important. Same principles on R3 forceps, exactly the same thing. Again, making sure that the serrations are intact. Needle holders, checking the tungsten carbide is intact, making sure there's no chipping or damage on this. And you can do your drop test that I mentioned on the ratchets, making sure they don't jump off the racks from around 30 centimeters. And when they're repairing, doing your due diligence, making sure your repairer knows what they're doing and they're using the correct techniques. Because if you heat up those devices and get them too hot, then they can lose the temper in the steel and that can make them too soft. So that's very important. Again, just really similar themes. Dissecting and delicate tissue forceps, just making sure the teeth crossover, are they still intact? Are they still doing what they should be doing? Bipolar and monopolar forceps, something that's quite interesting because we see quite a lot that from overzealous brushing and cleaning of these, particularly if you're using like you might be using a metallic brush or something like that, you can easily damage this coating, and obviously we don't want this. These should be routinely insulation testing. We've got a really good insulation tester we use in house, but they can be checked manually just to make sure that there's no obvious damage to the surface, because we don't want any current leakage. But vital that you are checking and testing your laparoscopic instruments, because these can potentially be causing damage internally to patients without the surgeon knowing. So in my opinion, it's essential that they're tested on a machine to check for current leakage. So repair quality, we see a variety of different repair quality. This is a really expensive Stilly type scissor that has had an attempted repair on the supercut edge, which looks is an appalling attempt. So repair quality should equal optimal clinical performance. This won't do the required job. This is what it should look like, as I showed you earlier. And I encourage sort of our team to mention the ICE principle. So that is for anyone having repairs carried out to inspect those repairs when they get them back from the repairer. Challenge, ask how they're doing it, who's doing it, are they trained, and also evaluate once you've had a repair done. Send it out to an end user, get them to check it. Are they happy with it? Is it up to standard? So that's really important. So refurbishment, I mentioned regarding the surface finish of the device themselves, and you can see here what can be achieved. I've actually got an after and before, the wrong way round, but you can see here that through refurbishing the device you can remove scratches and marks and create a really beautiful mallet once again by applying important and crucial grinding and polishing and taking back that surface finish to that really smooth under 0.2 micron finish, and also has a benefit for protein. And just to show another yucky image of some rongers, of course, the vital part of the repair and refurbishment is also to reduce the risk of surgical site infections and protein residue. In this case, there was a surgical site infection as a result of an uncleaned instrument. Just conscious, I'm running towards the hour, so I've got quite a few more slides to go through yet. So some examples of surface condition. So this is your box joint, and early on we discussed the box joint and how sometimes this can be a bit of a pain in relation to the original design of the Spencer Wells screw joint. But this is just to show an example. We took apart some box joints, and you can see where these devices haven't been perhaps dried correctly, and perhaps they weren't finished particularly well originally, and obviously you can see a rough finish here. Therefore, water is going to sit on it. It's not going to dissipate, and potentially it's going to start a corrosion process. So really important that all your devices are finished to the highest standard inside the box joints as well. Sometimes we see things that shouldn't be on surgical sets, and they can affect other instruments. This was a rusty stationary bulldog clip that was found on a surgical tray. This should be from a stationary supplier, your Staples. But this had actually washed rust all over the other instruments, and you can see here on a retractor and on the inside of another retractor here, rust residue sitting on those devices. Tape is a big no-no for me. So it's a great way of identifying instruments, but if some of that tape peels off, then you're potentially in surgery. That area of the device isn't sterile, so that's a big no-no. Bugs can sit under it. It's just not a great thing for the cleanliness of the device. You can see another example of an instrument in use that shouldn't be in use here. So this should be a nice gold plating, similar to this one, but that's been damaged as well and oxidized. So again, that should be taken out of use. Different colors are interesting as well. This is a example of silicate deposits. We've got like a rainbow effect here, and indeed a crack on the here as well. But just to sort of show you that you can get different colors, and I've seen studies that actually showed that although you might get some different colorings, they're not. It doesn't mean that they're not safe to use. I have some details on a study of that I can share if anybody's interested. Cracks can be avoided with lubrication, if ensuring those devices are moving freely. So just to show you, so looking at some poor repair techniques, I've mentioned the scissors already. Unskilled grinding, cutting right into the scissor. This scissor then can't cut where it needs to cut and will have to be thrown away. Arthroscopy punch here should be nice and sharp, nice fine sharp edge like on the right here, but has been poorly ground and again cut into. Look at that, how that's been cut into there, and you can see the flat that's been put on it, which obviously when the surgeon gets it isn't going to do what it needs to do in the knee. And then some gouges that have just been destroyed, the complete edge ground off of them. This is what it should look like, a nice hollow here that has got a nice sharpened edge, but these have literally just been flattened on a linisher and with no skill at all. So again, if that turned up in Mr. Capener's hands, I'm sure he wouldn't be very happy, because of course the device isn't looking how it should be and it's not going to do what it needs to do. Crack dissecting forceps, quite a common thing. We see cracks on dissecting forceps that obviously, again, this is just something to watch and keep an eye on. Needle holder, I mentioned keep trying to look at your needle holders and look at your tungsten carbide inserts. This visually just looked like a rusty instrument on the tip, but when we zoomed in, we could see that the tip was damaged. Some of it's been taken away and it's left an unfinished surface underneath. Free irons released, as we mentioned earlier, that as it likes to do, and you have this rust. So it's important to inspect your anything which doesn't look right. It might be worth a look under magnification, because there might be another story to be told there. Saline is a nice instrument killer and is widely used in cardiovascular thoracic surgery, and would love to find an alternative to this. So these are some really expensive vascular scissors, and you can see where the surgeon's been holding these on the grips. They've started to tarnish, and these are like the highest, probably some of the highest quality stainless steel you're going to get, but saline will cause damage to this if it's not washed off immediately after use, which quite often it isn't. I've got an example here of a mild steel nut being used. So here we have again I guess a repair that's been done, or might be a device that's been manufactured. The rest of it has been manufactured from the correct 420 stainless. This and then unfortunately this is mild steel, so this has gone rusty because it's not to your ISO 7153. So last couple of slides here, understanding IFUs, and I just wanted to put this up because I think there's going to be, with the MDR, there's going to be more and more emphasis on understanding how to clean and sterilize devices. Here's a kerosene, and I've shown a couple of examples of rongers, but quite often there's obvious descriptions here to describe how to release a device so it can be cleaned. But if you're not sure, always ask the manufacturer if there is a way to disassemble a device so it can be cleaned correctly. Because IFUs aren't always the easiest to follow, so it's always best to consult on that. Protecting instruments is key, and reflecting back to a slide slightly earlier when we were looking at sustainability. So obviously part of sustainability is circular economy, making sure we're not throwing away devices unnecessarily. So to do this, initially we want to make sure they don't get damaged. To give them the best shot of that, we want to protect them. So if you've got delicate instruments, and in this picture here, it's a really nice handset with a few delicate tissue hooks and forceps. They can be put in a basket with silicone protection. This can be customized and fitted to them to protect them. This is a great first step, because before you have to repair the device. Why look at repairing a device when you can actually prevent that in the first place? And this is obviously very important, and something that a lot more people are considering nowadays. Tools to consider. So you might consider getting something like this, an inspection kit for your instruments. You can also do some testing with this. There's also some textbooks, World of Surgical Instruments, would recommend that for some further tips. Industry guidance, you've got the AKI, which is a German organisation, Red Book for surgical instruments. So I'd recommend having a look at that. That gives a lot of in situ guidance, and the newly updated ABHI Surgical Instrument Purchase and Care Guide. I'm happy to try and share links for both of these if anybody wishes. So in summary, instruments are crafted by makers and technicians that are related to cavemen, vaguely, you might remember. Names of devices come from the inventors. Iron makes up the majority of the composition of the device, very important from the understanding how we can ensure that devices are maintained. Passivation of the steel is crucial. That comes from the correct composition of the steel, and that all parts are to ISO 7153, not just the main bod of the instrument, but any part. Think back a couple of slides to the rusty nut that we showed. Variety of craft processes are used for repair and manufacture. Consideration must be given to sustainability. One thing I was going to say, but I didn't mention, obviously, when we're thinking about sustainability, there is a drive to try and repair everything, but we've got to consider safety first. If the device can't be repaired safely, or there isn't the correct level of skill for the person carrying out this, then we shouldn't repair it. We probably should replace it. So that's something to bear in mind. Repair quality, in my opinion, should be equal to the OEM. Surface finish and functionality, when we're looking at condition of instruments, should be considered separately. So we're looking at what the surface finish looks like from a corrosion perspective, and also the functionality of the device. Can it cut? Is the forcep action working correctly? So they're two quite distinct things. Surface finish can be picked up by refurbishment, which is actually reworking the surface of the steel, not just sandblasting it and covering up all the cracks, but actually reworking that, and that's vitally important. Basic regular checks can mean safer surgery sets overall. And final comment, buy some lubricant for your instruments. There are some good surgical lubricants out there, and they should be applied to devices. You're talking about mechanical working parts, and they will bind up. They will then get things like fretting corrosion. If a surface or a box joint is rubbing together, that will lead to damage to the passive layer of the steel. That will then leak free iron. So really vitally important that where they need to be, devices are lubricated. And just finally, some dates for your diary. Many thanks for listening. So that's the end of the session. I'm just going to jump on and see if we've got any questions along the way. There's my email address down the bottom. If you've got any questions, please email me directly. And here's the dates for your diary for our next two sessions. So the 24th of April, we have rigid endoscopes. So we'll be looking at education and usage of those. And 6th of June. So the rigid endoscopes is going to be done with my colleague Mark Pullen. And on the 6th of June, I have my other colleague Nick Williams, who's going to be covering introduction to flexible endoscopes. We're keen to get some input around the cleaning of the endoscopes. If anybody would like to contribute to the webinar, please drop me a line. But you should be able to click through these QR codes and register. So I'll just leave this slide up for a moment, so you can have a look at that. But yeah, thanks for listening, everybody. If there's things I've missed and you want to see them in webinars next time, then please stick it in the comments or send me a mail and we can discuss that. And I look forward to seeing you in the future at other webinars. So, right, great. We have got some questions coming in. So I'm going to start off here, and we've got a question from Anne-Marie, who's asked, and if I can't answer a question and it's something I can come back to you on, then I'll do that. So should instruments be rinsed off after use before sending off to be sterilized? In my opinion, yeah, because if they're covered in, there should be at least some pre-cleaning, because they could be covered in saline, as we mentioned, and that can obviously cause problems to the instruments in terms of them corroding, binding up. So yeah, if that's possible, definitely yes. If not, is it also possible that that there could be some sort of pre-cleaning treatment? I've seen things like humid bags where you keep the instrument humid and make sure that residue doesn't die on them. So that's also important. So question for Solicity. No problem. Thanks. Very happy to do the presentation for everyone. When you carry out refurbishment of instruments, do you check the quality of steel and protein level? Does it come under the scope of remanufacturing or adding? So there's a couple of different questions on. So the first one, do we check the quality of steel? The only way we actually do that, we repassivate all the instruments, and that is our way of testing the steel. We could, if it was something somebody wanted, we could of course do due diligence on the steel, and we could send them away to a lab and have them tested. But in my opinion, if we put the instruments through our passivation process, you very quickly see if they're not to the correct specification. Quite often, if you put steel that's not got the correct amount of chromium in, the device will go black, it will discolor. So this is a good way to test this. We don't check the protein level, but again, this is something we can do. We've previously used a Pro Reveal and tried this, but there might be some other in situ tests that could also be used. So and Solicity's also asked, does refurbishment, does it come under remanufacturing? No, it doesn't. We're not fully refurbishing the device. We're not taking off the manufacturer's marks. In the case I'm talking generally about what we do, we're retaining those marks. We're ensuring that the device is following the original OEM specification. Remanufacturing is something that's interesting, and I'm seeing that come up a lot, particularly for some single-use devices, and that is taking the device away, and actually then that company would be accredited to manufacture that device and would remanufacture it and put it back under a CE mark or a UK CE mark back on the market. That is quite interesting. I think that's possibly something that could happen. The problem that I've seen with devices that have come to us and that we've been asked to CE mark when they're not CE marked is really just our concern around the origin of the original stainless steel, and if that stainless steel is to the correct levels. And we kind of summary that if the devices aren't CE marked, it's probably because often they're very good quality. They could be used, but they might have been purchased before CE came into force. But however, because they haven't got the CE mark in there, there's a slight concern that they might be not to the correct standards. So that's something we wouldn't do. Lisa has asked for the slides, and yeah, of course, I'm happy to send the slides. Key dots, I mean, yeah, I know they're widely used. Just from a manufacturing perspective, it's not something I would personally use. Just because if there might be no chance of it coming off, is there a slight chance that that the key dot could come off? Perhaps. I mean, obviously, other options are laser marking. Laser marking can also have its challenges if you don't passivate or treat the mark after you passivate, then potentially you can get rust. So there's pros and cons, but sticking things on instruments is, in my only my opinion, is not something that I would probably do. I would opt for laser marking. David, who I know is in the States. So hi, David. Thanks for joining us. And he said, when you carry out refurbishment, oh, right, okay, interesting. At the same, right, okay. I'm now getting confused by two questions. Ah, right, okay. There's no additional question there. So, David, if I've missed something there, sorry, but I'm just looking at the chat here and it looks like it's similar to Celesti's question. So, Aidan O'Brien, you mentioned to test scissors with manufacturer, recommend test materials. What test materials do you specify for your scissors and other instruments? Do you have a list of these test materials? So in the British Standards, it gives you test materials. They are quite old, so some of them are quite outdated. However, there are like-for-like test materials that you can use. The German instrument manufacturing, I think there's a industry group. They have their own. They created a DIN standard, DIN, that has particular test materials. So I think it's got a red test material and a yellow test material for different types of scissors. I think the yellow's for finer, but they'd be quite good. But obviously you'd have to then reference the DIN standard in your procedure. But again, we've got information on that. If you want to drop me a message, I'd be happy to share the information on that. Okay, so is there an in-house formula to create instrument milk? Not that I'm aware of, I'm afraid, on that one. So question around the sprays that are on the market to keep instruments moist as per HTM requirements. Can these damage the instruments? We've tried out a couple of them and haven't found them to damage the instrument, but I think it's like everything. You've got to do your due diligence and check that the spray you're going to use, how has that been tested? And sometimes I've seen then people have referenced that they've been tested on 316 steel, which is a completely different steel. So you might as well test it on plastic. So providing they're tested on stainless steel and they're correct, then they should be okay. The Some of the sprays, I've seen foams and things like that, but generally when we've done some very basic rudimentary in-house trials, I've not seen that they damaged the instruments. Certainly no more than not doing anything and leaving blood residue or saline on the instrument would do. Okay, where are we time wise? Sorry, I'm way over time, so apologies. Anyone can drop off when they wish, and I'll share the presentation. But while we've got some questions, I'll keep answering them. So, how widely do services repassivate instruments, and how can we avoid rusting instruments in areas when saline is in contact? So, I mean, I'm just speaking from our perspective in terms of services, and I'm not sure the just what might be directly referring to. I'm assuming we mean repair services, but I don't know. I can only speak for ourselves, and that's something that is an extra process that is done. I don't think it's widely done, because and obviously to do that you have to have the validated process. So that's the important part. So yeah, which in my opinion, if you're interfering with the surface of the steel, devices should be repassivated, because you are then risking disturbing the steel, releasing free iron, etc., etc. But I'm happy to give some more information on. Obviously, I can't speak for other companies, but we do it and it's important. So also another comment about how we can avoid rusting instruments. So trying to work with theatres, trying to encourage them to rinse off the saline, because you will 100% get rust if you're using saline. It's not being rinsed off. And because the other challenge is that a lot of these devices are often left in situ for a bit longer. So not only are they got in contact with saline potentially, that then they're in situ for a bit longer, so this saline will be sitting on them. So getting them rinsed off, or ideally getting something as an alternative to saline used would be good. So I think so Chris has asked, we got here, material selection has prompted me to think about appropriate device marking technologies for applying the UDI measures. I'll be interested to hear your experience. Yeah, I mean, there's that. So Chris has made a comment about applying marking technology for UDI and how that is affected when you're thinking about marking the device. And yeah, it is a challenge, and that is something that will be even trickier, I think, for when you're marking a device with a UDI surgical instrument, and then you're putting it out there and it's going into use for maybe 10 years, and then revalidating that mark. How are you going to do that? That's where something like a key dot might, I suppose, if that was replaced regularly, that might give you a clarity of mark. But I think all you can do is do a validated process where you're laser marking, and then you're cleaning the free iron, so you're oxidizing the layer, and you're checking that, and obviously I think Chris has, from GS1, making sure that's a correct GS1 mark, and then assuming that we may then also be using these marks for tracking, making sure that they can be scanned at sterile services. But that's certainly something that is going to need further work, because there's all manner of different chemistries that come into contact, and as we mentioned, water quality, that's going to provide these challenges. Okay, so I don't know if we've got any more questions. I'll just go back into the Q&A again, and what I'll also do is just stick up that slide again, just so you can see that. So you can see that in case anyone wants to take the details just of those of the next sessions. And it's 3:10 now, and I don't think we have any more questions on the Q&A. So I will say thank you very much, everyone, for attending today, and please, if you've got any feedback, drop me a line, and we look forward to seeing you at the next session. I hope everyone's enjoyed it. If there's things you've missed and you want to hear about in the future, then please fire over anything. That's no problem. Great. Take care, everyone. Thank you.